Hey everybody, Chaz Underreiner here, and today we are going to talk about digital audio. So let's get started. First of all, just to talk about the recording process, we have four basic steps. We have tracking, which is actually setting up microphones or having some kind of input come in and recording that thing into electromagnetic signal on tape, into digital information or whatever. Then we add effects onto that, we mix and we edit those together, and then we master recordings to be distributed. So here's the basic explanation of that. Adding effects like EQ, delay, mixing and editing, so that's splicing together different takes into one unified take. So let's talk about how this was before the dawn of computers, with analog signal, meaning with electric signal. So sound pressure level of audio is transduced into voltage. That means that sound pressure waves in the air, compression and rarefaction of air molecules, is transduced by a microphone into electricity. The signal flow can be kind of intense. The frequency and the amplitude of the signal can potentially change and be degraded at every step of the signal chain. So let's look at a signal chain. Here's an example. So we've got a microphone. Whenever you plug that microphone into anything, there is a pre-amplifier, an analog amplifier that boosts the signal. We have a bus, blah, blah, blah. We're going into some kind of recorder. Let's call it a tape machine for now, since we're talking about analog. Then we go to another amplifier, another fader, master fader, a control room level, another amplifier, and then some speakers. So just to get a microphone to go into speakers, we go through many steps in analog, which can be great. Is not actually a problem, but it could be a problem because we could potentially have noise or some kind of interference in any of these spots. So the signal flow is just a little bit complicated. Also with analog, we have these sweet VU meters. To me, it kind of looks like, makes you feel like I'm on a submarine or something. See the needle going back and forth. And then we use oscilloscopes to see, basically to zoom in and see what the sound wave is doing in time. And whenever recordings were made, so let's say we recorded, my band goes into the studio, get into some famous studio, and we record an album. Those recordings are going to be written into tape, and then all of those recordings together will be made into a master. So a master tape, that's where that comes from, mastering, or a master. So we make copies of this master in order to distribute it out into the world. So, for example, here is a master tape for Prokofiev's Classical Symphony, made by the OSR. I'm not sure which orchestra that would be, but it's in Switzerland, in Geneva, recorded in 1961. And you can see here there are different movements, different takes, and then some notes that the engineer made about all this. So this physical object is the definitive version of this recording session, and of this album that was made. So this is cool. It's going to sound great. It's written to tape. It was made in a real studio. But this physical object can be degraded, can be lost, can be damaged or destroyed. So potentially the original master of something can be lost if it's physical. This is different in digital audio. So in digital audio, we take an analog audio signal like voltage, and we encode it, process it, store it, and reproduce it, all using binary, the basic language of computers, which is a bunch of zeros and ones. The way that this happens is called sampling or pulse code modulation. And basically, whenever you have a sound wave coming in, you have this smooth, continuous change in voltage. That sound wave gets measured a bunch of times, and each measurement gets saved as a data point. So, in the world, in acoustics, sound is waves of air pressure, as we've discussed before. Whenever that gets transduced into analog, it gets turned into electricity. And then whenever that gets turned into digital information, it gets turned into binary or into data. So most of the time on your computer, whenever you're listening to music, there is, or you're working with music, you're working with audio, you're working with digital audio. So what's happening is that, let's say I play back something on my computer, I play some audio. Whenever it goes from my computer to the computer speakers or to my headphones or whatever I'm listening with, it actually changes from binary back into voltage. And then that gets sent into, let's say, headphones. And then the headphones turn the voltage back into sound pressure level, back into acoustic information. So this conversion of SPL to voltage to binary, and then binary back to voltage, back to SPL, happens all the time in our daily lives. We don't even we take it completely for granted, basically. So binary, let's talk about binary. Basically, binary is a string of zeros and ones. And each 0 or 1 stands for, can potentially stand for a bunch of things. Each digit or bit, so each space that's potentially a 0 or a 1, has the power of 2. If you have more than one bit in a row, that's called a bit word. If we have 8 zeros or ones in a row, that is called an 8-bit word, or a byte for short, B-Y-T-E. And a byte should sound familiar because our files are often kilobytes, megabytes, gigabytes, terabytes, etc. We deal with those all the time. So the basic way that this works, let's say right here we have a byte or an 8-bit word. So we have a string of 8 bits altogether. We number them from right to left. So this is bit number 0, 1, 2, 3, 4, 5, 6, 7. Since we're talking about computers, we always start counting at 0, not at 1. And so each of these bits has a power of 2, right? So if bit number 1 is a 0, it always counts for a 0. And if it's a 1, it can count for the number 1. If this second bit right here, bit number 1, if that's a 0, it counts for 0. But if it's a 1, it counts for the number 2. And so on. So this bit can count for the number 4. This bit can count for the number 8, 16, 32, 64, 128, etc. So the reason that this is that we have 2 to the 0 power equals 1, 2 to the first power, so 2 times 1 equals 2, 2 squared, so 2 times 2 equals 4, 2 to the power of 3 is 8, 2 to the power of 4 is 16, and so on. So all of these just count for multiples of 2. What that means is that we could potentially, if we have these 8 bits, if we have a byte, these, if I make all of them 1, can add up to be 255. So we have between 0 and 255 can be counted or represented using just 8 bits. We can also count this on our fingers. So you could think of your pinky, your right pinky as 0 or 1, your right ring finger as 0 or 2, and so on. So that can just be a visual aid to help you count this stuff. So let's count something. If we wanted to get the number 28 in binary, we would need 5 bits, and we could add it together using 16, 8, and 4. So 28 in binary would be 1, 1, 1, 0, 0. Pretty simple. It's just multiples of 2 added together. So binary can stand for numbers, like we were just talking about. Binary can also stand for numbers and letters. So that's called hexadecimal counting rather than decimal counting. So think about a Word document. If I say, "What's up?" in a Word document, the letter W can be represented using just binary. So what happens basically in a word processor is that every letter, number, etc. is saved as just a combination of zeros and ones in the data. Okay, so let's talk about different bit sizes. So an 8-bit word or byte is 256 possible numbers, right? If we add another one onto the end, it goes up exponentially because we're talking about exponents of 2, right? So an 8-bit word has 256 steps. If we have a 16-bit word, now we have 65,536 steps. So this is why computers are so powerful. If you just add on more processing power, if you make bits longer, you get now exponential growth in what the computer can handle. 24-bit word is 16 million, and so on. So this is really important for digital audio, and this binary counting, these bit words, go into one aspect of digital audio called quantization. Okay, so sampling. The way that analog audio, the way electricity gets turned into data is through measurement. So every time you have a wave, it gets periodically measured and then saved as data. So periodically means it's basically even, it's at a given rate, and we call that rate a sample rate. Another way to understand this is the vertical aspect of digital audio, or frequency. Okay, so here's our wave, and we measure it at a consistent rate over this time. So let's say this is 1 second. This whole thing that I'm looking at is 1 second. Then our sample rate would be however many points there are. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I probably miscounted, but let's say 20 sample rate. So now we are measuring our incoming wave at 20 sample rate. And sample rate's really important. How often you measure a wave per second basically means how good you are at measuring, how good your overall result will be. So here's our original waveform. Electricity has consistent output of voltage. If I sample it twice, this is not a good representation of the original, right? It's like it doesn't look the same. There's no way it would sound the same. If I measure it a couple more times, it starts to look more realistic. If I measure it even more times, it'll look even more realistic. So you see the idea. We have to do a lot of samples per second for it to look realistic and for it to sound realistic. Because, here's the thing, if I don't measure fast enough for my samples, like let's say here's my wave and then my sample rate is this fast. If we connect these together, if we draw a line between those red things, those red dots, it's not going to look like the original wave at all. It's going to look all janky and weird. So it also wouldn't sound like the original wave if we're talking about sound recording. So basically, the higher the sample rate, the more measurements you have per second, and the more true to reality the recording is. So to summarize about sampling, with analog, signals are recorded, stored, and reproduced as changes in voltage, usually through electromagnetism. And then in digital recording, the signal is sampled at a given rate. Each sample is a data point that gets saved in binary. And so sample rate is the number of measurements that are periodically performed per second. And this is kind of like frame rate in video. So if we look at some CCTV camera footage, if you have 1 frame per second, it just looks like a bunch of still photos that are put one after the other, right? If we have 5 frames per second, you can see something like movement. It looks super choppy. It still looks like a bunch of still images, but they start to connect together a little bit. If you go up to 7.5 frames per second, it looks a little better than 5 frames per second, but it's still kind of choppy and weird. Like if you saw anybody moving like this in real life, it would be terrifying. Or they're an amazing dancer, like doing some hip hop dancing. 15 frames per second, this starts to look like real life. It's almost convincing. So watch 15 frames per second. Still looks a little bit strange in terms of the continuity, but it's not bad. And then 30 frames per second, 24 frames per second is the threshold for our eye to believe that images are continuous. And 30 frames per second crushes that. This looks like realistic movement. You can really see it with the hand wave. So the same thing applies for animation. If we have an animation at 15 frames per second, it looks pretty good, but it's also kind of choppy. You can hear my dog walking around in the background here. Go lay down. Chill. At 30 frames per second, which is twice the amount of work, it looks a lot more continuous, a lot more convincing motion. And then at 4 times the work, 60 frames per second, this looks totally convincing, totally beautifully continuous. So you can tell how much labor has gone into animation by how many frames there are per second, and it really affects the motion significantly. I'm a huge fan of Japanese animation. And Japanese animation, they usually do slower frame rates, but they do more detail on each frame. Whereas Western style animation, they usually do a lot of frames, so having really good motion, but with simpler characters, for what it's worth. So here are some common sample rates with audio. So telephony, telephones use 8,000 measurements per second, or 8 kilohertz sample rate. So that quality, the kind of low quality telephone signal has the least number of samples that you can use. The normal CD quality sample rate is 44,100 measurements per second, or 44.1 kilohertz. Is it kilohertz? Whatever. K hertz. The frame rate for video and film is 48,000 measurements per second. And then we have some higher ones, like 96,000 measurements per second sample rate is often used for classical music recordings and high def recordings. Okay, so that's how often we're measuring. I said that sample rate is the y-axis. Actually, it makes more sense to think of it as the x-axis, this axis. The quantization rate is the y-axis, if we're thinking about a wave. And so quantization is not how often do we measure, but it's how many steps do we have to save that measurement. So it's the amplitude component of the sampling process, and it's measured in bits. So with sampling, we're talking about frequency, and with quantization, we're talking about amplitude. So these are the two most important, basically, aspects of sound, and so we treat them differently with digital audio recording. So these three pictures are all with the same sample rate, measuring it 10 times within the image that we can see, but they all have a different quantization or a different bit rate. So this image right here has 3 steps. So this is a 2-bit rate, because we have 0, 1, or -1, basically. So this is not realistic. So even though our sample rate's pretty good, if our bit rate isn't good, it won't represent the signal very well. So this has 5 steps of measurement. So we add another 0 or 1 onto our measurement, another bit, then we get that much better of an image. if we add, so 1, 2, 3, 4, 5, 6, 7, 8, 9. So now we have 9 steps of measurement. It represents the wave even better. So here are the bit rates, the bit sizes that are commonly used in audio. 8-bit is, again, as we talked about, it can represent 256 steps. So now with a wave, we're talking about we can measure it, we can measure the voltage in 256 possible values. With 16-bit, we get 65,000. That's a lot more. And so on. 24-bit, we have 16 million. So 8-bit was a bit rate that was often used in early video game console systems like the Nintendo Entertainment System, NES. 16-bit is commonly used for CD quality audio and is used on most video game consoles now. And 24-bit is the standard for film and video, and also because it synchronizes better with the 48K sample rate. So the greater the bit depth, the less the errors are in conversion. So these are the sample rates and bit rates you need to know. These are very important. So CD quality is 44K sample rate, 16-bit. Video quality is 48K sample rate, 24-bit. Let's listen really quick to, oh, actually I didn't need to get out of that. Let's listen to the difference between these different bit rates. So for one thing, one way that I like to do this is video game music, because I love video game music. So if we listen to an NES video game track, so let's say the original Super Mario Brothers. Yeah, here we go. Okay, so in 8-bit, it's very charming. I love the sound of 8-bit music. But because the bit rate is so low, because we only have 256 steps to represent audio, it doesn't sound very realistic, right? So like if you listen to the instruments that are being played, the is trying to be the sound of a snare drum. It's the snare drum, it's the best snare drum sound you can get on the Nintendo Entertainment System because of the bitrate partially. So it sounds great, but it doesn't sound like an actual snare drum, right? So very charming, but not very realistic. Let's check out from Super Mario All-Stars, which is on the Super Nintendo, the same theme, but played in 16 bits. On the Super Nintendo Entertainment System. So it sounds a lot more realistic, right? Like the hi-hat sound sounds way more like those actual instruments. You also have a kick drum in there, and it sounds like a pretty good version of a kick drum. It's only it's still not completely CD quality for various reasons that have to do with like the way the Super Nintendo works, but it's pretty good. And then if we go to a totally CD quality version, like let's see, Mario Overworld theme in 64 or the GameCube or whatever. I don't know. Okay, Super Mario 64.
It's me, Mario.
Okay, so still using MIDI instruments, but now we're close to CD quality. We're actually, this is CD quality in terms of sample rate and bit rate, and so we have a big jump in overall audio quality. So listen to these just like right next to each other one more time, so you can hear the difference between 8-bit, 16-bit, and better. So I think that illustrates it pretty clearly how bitrate is really important for the overall quality of audio. Something that can happen if your bitrate isn't high enough is that your values, your measurements, will get rounded up or down. So like if you see right here, this right here is a little bit above this line, but it'll get rounded up or down depending on how good your bitrate is, and that will cause some issues. So whenever we're talking about any kind of digital audio, the dynamic range is limited because it's limited to how many steps of measurement you have. Even if you have 500 million steps of measurement, it's still limited, and it's stepped. So it's not continuous like analog audio is. So the most common form of digital audio encoding, this whole process of sampling, is called pulse code modulation. So the way a computer actually does this. And what it does is it takes the original sound wave and then it periodically puts out a pulse, and then that pulse gets changed or modulated by the wave. So now our pulses are all shaped by the amplitude of the wave. So this image right here is called pulse amplitude modulation. So computers are good at some things and not good at others. Putting out a pulse and then taking measurements in zeros and ones, a computer can nail that. So that's how it does it. Basically, pulse code modulation will represent binary in a string of ups or downs in terms of a line. So the analog signal is sampled, binary number is stored, and then these pulses represent the signal. So digital numbers are stored in a file with a header, and so it tells the computer, it tells the machine how to interpret these big chunks of zeros and ones. So here's an example. We have our analog signal. That signal modulates some pulses. Those pulses get changed into binary and to these the series of on and off messages. Something like that. Okay. So if this goes wrong, for some reason, there could be a couple reasons, it's called digital aliasing. So aliasing meaning it's like an error. So here are a couple examples. So this is a helicopter flying, and the blades appear to be not moving. This is a car wheel moving, and it looks like the hubcap is moving in different directions. It'll kind of like slow down and then go one way. So this happens because the frame rate of the camera isn't fast enough to capture the movement, the speed that it's doing. So like even if I do like this, just the speed of this camera right now, I think is 30 frames per second, but because of the encoding and stuff I have, it's doing slower. It's the same thing. So it's all about capturing speed. Aliasing can also happen, I want you to see this in full screen. Aliasing can also happen depending on how many pixels you have. So less pixels looks more pixelated. You can see the pixels more, and it looks less real. If we add some more pixels, we get a more realistic unicorn. And if we add lots of pixels, then oh my god, we get the most amazing unicorn possible. So there's definitely charm. Like all of these can be used in different ways. I find 8-bit stuff very charming, but if you want to create realism, you need more pixels, you need more measurement. Here's another example. So here's the best-selling jazz album of all time, Kind of Blue by Miles Davis, which is great. You should check it out. So if we can only represent that using 4 pixels, this is the album cover. It doesn't look very convincing, right? So the more pixels we get, the better our sample rate is, then the more realistic the image gets. And aliasing with audio can happen because of some kind of confusion in the recording process, either by not having a high enough sample rate or bit rate or something else. So let's check out this undersampled recording. Okay, so that's a recording of a band made that doesn't have the correct sample rate. Let's listen to it with a correct sample rate.
Last night or the night before that, I won't say which night, a seaman friend of mine.
In terms of quality, basically the undersampled version is unacceptable. It sounds like it's underwater. I can't hear a bunch of stuff. There's a ton of instruments that just don't come through at all. And then with the higher sample rate, it sounds much better. You can actually see the difference in the waves here between how much data it's capturing. So in order to prevent these sampling errors, in audio we have what's called the Nyquist theorem. So go ahead and read the Nyquist theorem. It says that the frequency bandwidth has to be twice as high as the highest frequency to be recorded. So if you know what the human range of hearing is, which you should, then you know what the Nyquist theorem says. So the human range of hearing is from 20 hertz to 20,000 hertz. So 20,000 times 2 is 40,000. So according to the Nyquist theorem, to make a recording that sounds good enough, that's faithfully encoded, we have to record with a sample rate of at least 40,000 measurements per second. And this is what we do. So we have what's called a Nyquist filter as well. That's because if you don't measure high enough, frequencies will actually reflect down and make kind of ghost sounds that shouldn't be there. So look right here. So here's our sample rate, and here's 2 times our sample rate. If our sample rate is, let's say 20,000, so not high enough, then the original, it'll act like a ceiling. The frequency needs to be measured above it, so it'll just reflect down and create an aliased frequency, or like a ghost frequency, at 13K that shouldn't be there. So measuring twice as much as we need to, twice as much as the highest frequency, and also putting a little filter on it will eliminate that problem. So digital audio is definitely different than analog audio for a variety of ways. Digital processing isn't permanent. It's cheaper to use digital audio. It's easier to transfer files, and you don't have to splice tape. But both analog and digital audio are used for different things. So that's it for this this talk about digital audio. I recommend you spend some time getting familiar with binary and appreciate what you have.